An improved method for ground vibration testing of aircraft structures has been developed by Boeing under contract to the United States Air Force. Among several innovations, the use of single-point excitation frequency response analysis, the application of computer technology in both the collection and analysis of data, and the method of supporting the aircraft during test were especially significant features of the program. The test aircraft, an A-10 defueled and fitted with dummy engines and with its landing gear retracted, was supported in a specially developed soft support system. This system consisted of 3 concrete support blocks, each fitted with a commercially available pneumatic air spring. The air springs, which included constant leveling pneumatic feedback, were attached to the aircraft at 3 points, one on either side at the fore-body jacking points, and the third one under the aircraft at the aft body jacking point. Objectives of the soft support system were to provide a stable test platform and, at the same time, to obtain adequate frequency separation between the elastic modes of the aircraft. A 10-to-1 frequency separation was achieved between the rigid body roll mode, measured at 0.4 hertz, and the first elastic bending mode of the wing, measured at 6.0 hertz. The stability of the soft support system was evidenced by the rapid decay of roll oscillations once induced by external action. The soft support system also made it possible to obtain a full set of dynamic characteristics for the entire aircraft each time the excitation point was changed. 100 accelerometers located throughout the aircraft responded to the single-point excitation forces to provide this comprehensive data. 10 single-point excitation points were selected, 5 on the main surfaces of the aircraft and 5 on its control surfaces. A typical measurement was accomplished by applying a shaking force to a single point on the aircraft structure. The vibratory response of the airframe to the shaking force was sensed by the accelerometers located throughout the aircraft. A previously developed computer program supervised the excitation, online data processing, and the recording functions necessary to the measurement phase of the test program. Electronic signals from the force gauge and the accelerometers were processed through signal conditioning equipment, a digitizer multiplexer unit, and a computer, then recorded in digital form on magnetic tape. Selected signals were routed to a modal analyzer system. Excitation signals were delivered to the shaker control panel from any one of 3 sources: a random noise generator, a sine wave generator, or from the modal analyzer's computer. The excitation signals were amplified to provide the desired force levels to the shaker. Waveform as well as force level were monitored to rule out undesirable distortions, and waveform and amplitudes from every accelerometer were displayed on monitor oscilloscopes to ensure continued high signal quality. The online data processing function of the modal analysis system is of particular importance because it provides assurance that the data, which have been recorded, contain information on all of the structural dynamic characteristics of the aircraft for the entire frequency range of interest. 2 specialized applications of random noise were used as the excitation signal formats for most of this test. The first is random transient, in which random noise excitation was applied to the aircraft for 8 seconds, followed by 2 seconds of no force while the excited vibrations died out. The second format used is called pure random or continuous random. In pure or continuous random excitation, random noise is continuously applied for a period of time. In this test, pure random excitation was usually performed for 40 minutes for a data set. The highest quality data from this test was acquired during runs at quite low excitation force levels. For example, the best data from the wingtip excitation point on this 26,000-pound aircraft was with 5 pounds RMS excitation force. At this input force level, although the resultant motion of the aircraft was very small, the aircraft response was quite linear, and the output signal-to-noise ratios were very good. Once the time history data were recorded, the measurement phase of the testing was complete, and activities at the ground vibration test site were concluded. The analysis phase of the test was conducted in the data processing room of the vibration laboratory. The time history test data were transferred from magnetic tape into the modal analyzer system. Each data record was visually checked to see if it was acceptable for further analysis. The time history data, in digital form, was transformed to the frequency domain by the modal analyzer computer, and the resultant frequency response functions were used to develop the linear system characteristics of the aircraft. The engineer begins this curve-fitting process by selecting computer programs from a pre-programmed family of algorithms which contain natural frequency, damping, and mode shapes as unknowns. The choice and use of algorithms is at the discretion of the test engineer and is the most subjective part of the test. The mode shapes are displayed on the modal analyzer CRT, and the modal data can be hard copied for use in documentation. The concepts developed in this program demonstrated substantial improvements in efficiency in all aspects of testing, and at the same time provided reliable, high-quality test data.